Hi, so I've got a project coming up that is going to need to do remote temperature sensing of various objects, and one of the techniques that I was looking at using to accomplish this was something known as remote diode temperature sensing. This is a very commonly used technique for measuring CPU die temperatures on PC motherboards. The basic premise on which it works is the CPU manufacturer will provide a thermal diode, something known as a thermal diode. It's no different than any other PN junction other than the fact that it's quite well characterized, so its properties are well known. And this interfaces with an external device which essentially uses a current injection and voltage measurement method to determine the temperature of that PN junction with quite decent accuracy and precision. So this is a technique that I was looking at using because it's quite low cost as well, as long as and it can be precise, very precise, as long as you've done the design correctly. There's not a huge amount of material that covers this though, so I thought it might be an interesting video just to explain how they actually achieve this, because inherently silicon or semiconductor devices are quite temperature sensitive, so it's a little bit puzzling when you first think about it how they're able to actually leverage these devices to perform thermal measurement when there's such large differences in their performance based on temperature, among other variables as well, of course, but temperature is a big contributor. So I think I'll start by just drawing out what the typical architecture of one of these devices looks like. So you'll start with your measurement device. So this is external to or remote to your sensing element, which basically has two terminals that it interfaces through. So we'll call those D plus and D minus. And internally, these are current sources and sinks, respectively. So there's essentially a current loop that gets made with the external PN junction, where a known, very controlled current is output from D plus and then received back through D minus. So its connection is actually quite simple. So you essentially have your thermal diode connected between those two pins, and you have some loop current ID. Again, very tightly controlled, passing through that diode junction. It doesn't actually have to be a diode either. So very commonly, they'll actually use a diode-connected BJT as well. So if we just pretend that that first device doesn't exist. So I'll use a PNP transistor for my example, but there's no reason why you couldn't do this with an NPN either. So I'll have it connected in this fashion. So you can see that virtually there's still a PN junction formed in here. So a forward bias diode going from the emitter to the base. So I'll just draw that a little bit more clearly there. So the base connects to the receiving terminal of the current sink of the device. And what they're essentially doing is once they've induced this current through this loop, they measure the voltage across those terminals, and somehow they are able to determine the temperature of the device using just that single measurement and the known current source. So in order to explain how they're actually achieving this, I think it's probably easiest. Unfortunately, we are going to have to look at the math a little bit for this. There's no way around it, but I'll try and keep it as simple as possible. But we will need to explore one of the fundamental equations of a PN junction or a diode, which is known as the Shockley diode equation. So you might already be familiar with this, but the basic form of the Shockley diode equation is the diode current ID is equal to the saturation current of the diode. This is also often referred to as the reverse leakage current of the device. It's not exactly that parameter for real diodes, but for ideal diodes, it's analogous to the reverse leakage current of the device, multiplied by e to the power of Vd divided by eta Vt minus 1. So what are these parameters? So we said ID is equal to the diode current. IS is the saturation current. And we've got Vd, which is our voltage drop across the diode. Vt, which is the thermal voltage of the diode. And we have eta, poorly drawn, which is our non-ideality factor. And that's it. And then we've got a minus 1. So how do these equations actually, how does this equation actually help us? Well, I think to start with, what we might do is just rearrange this. So we're kind of looking at it in perspective of the inputs that we have to this circuit, as well as the points that we're measuring. So that is going to be our diode current, which we're inducing, and it's going to be our diode voltage, which we're measuring, Vd. So we'll just move over to this side, and we'll rearrange that. So first thing I'm going to do is I'm going to divide both sides by Is. So we'll go ID divided by Is is equal to E to the Vd divided by eta Vt minus 1. And then we'll add 1 to both sides to move the 1 over. E to the Vd divided by eta Vt equals ID divided by Is plus 1. And we're just going to make a simplification here because, well, we don't need to. I suppose we could use it as it is, but the assumption is going to be that ID is much, much larger than Is, and typically that is going to be the case. This reverse leakage current, or the saturation current, is a very, very small figure compared to the magnitude of the current that's running through this loop. So for all intents and purposes, the proportion here is dominated by this ID divided by Is, and this 1 is essentially negligible. So we'll neglect that, and we'll take the natural log of both sides to take this fraction, bring this fraction on its own. So Vd divided by eta times Vt equals the natural log of ID divided by Is. And the last thing we'll do is we'll bring the eta and the Vt across to the other side by multiplying it out. Eta times Vt multiplied by the natural log of ID over Is. Okay, so this is our first equation. It's the same as this one up here, just rearranged. And we're going to introduce one other equation to simplify this V, or to express this Vt in other terms. So the thermal voltage of the diode can be, so we'll label this as equation 1. Thermal voltage of the diode can be expressed as kT over Q. Now what is this? So in this case, in this equation, K is a constant known as the Boltzmann constant. and Q is the charge of an electron, so electron charge. And T, lastly, is our absolute temperature. Now this might be starting to make some sense now, why we're making this substitution. So if we substitute this now in for Vt, we end up with the equation Vd is equal to eta Kt over Q ln of Id divided by Is. This is our second equation. Now, this might not seem to help us much. I mean, it's a little bit clearer, I suppose. We have something now that relates our voltage drop across the diode to our temperature as a function of some current that we're injecting in this thing, but it doesn't really help us because even though we have all of these constants here, we don't have anything that links these two proportions together in any way. So Vd could be anything, given that you're not you aren't in control of, or rather, you have no knowledge of temperature, and you have no knowledge of you will have knowledge of this ideality factor, but non-ideality factor. However, this equation in itself is not enough to determine temperature. So what we're going to do here is now pretend that, or assume a value of ID1 for this ID. So we'll create two cases for ourselves. We're going to measure the voltage drop across the diode for one known current, and then we're going to measure it again for a second known current. And let's just assume that the proportion between the two currents that we're measuring at is 10 times. So we'll say ID 1 times n. So instead of 10, we'll just write some proportion, n, equals ID2. So we have our first measurement performed with a current of ID1, and a second measurement performed with a current of ID2. So in order to determine the temperature, here's what we do. We take Vd at some known current of ID1, so we'll call this Vd1 equals eta Kt over Q ln of ID1, ID1 divided by Is. And we'll take a second measurement of Vd2 using ID2. So same as before, eta Kt over Q ln of ID2, but instead of ID2, we're going to write ID1 times n, because we have control over this current source. So we might make that 10 times larger, we might make it 100 times larger. The absolute proportionality doesn't matter in itself as long as you're aware of it in the design. So n times ID1 divided by Is. So the problem, again, is that these equations on themselves alone don't help us because we don't know what this saturation current is, and because it's a very, very small figure, which in turn makes the contents of this natural log a very, very large figure, having no knowledge of this and assuming its value is going to create a lot of error if we're wrong about our assumption. So our best course of action is to somehow eliminate that. So make IS something a value that we don't need to care about. And how do we do that? So we do have two natural logs here. We somehow need to cancel these. So we have IS in both terms. We have ID1 in both equations. And if you look up your log laws, the natural log of, so if we draw out the natural log of A divided by B is equal to the natural log of A minus the natural log of B. So let's try and get these into this form. So we'll subtract VD2 from VD1. So we'll do delta VD, we'll call that, is equal to VD1 minus VD2, which is equal to eta KT over Q ln of ID1 over IS minus eta KT over Q ln of N ID1 over IS. Now, might have to move up to the other corner for this, just so I have a little bit more room. But just before we do that, you can see that we have the same coefficient out the front of both of these. So we can simplify this a little bit further. So I'll do that up in the next corner. So we'll go delta VD is equal to eta KT over Q outside of, and we're going to, it looks terrible, we're going to apply our log law that was down here to simplify this now. So we're going to do the natural log, I'll move this down again, we're going to do the natural log of ID over IS minus the natural log of NID over IS. So that'll be natural log of ID1 over IS divided by N ID1 over IS. And what you can see here now is that we have like terms on both of these. So we can cancel these two terms. And then this simplifies down to delta VD is equal to eta KT over Q ln of 1 over N. So we know what N is. K and Q are constants. We measure delta VD, so we measure it at the first voltage and we measure it at the second voltage, so we know the difference between them. And eta is the only parameter left, and this is a parameter that again is very, very tightly controlled in the CPU's case. And as long as you pick a manufacturer of a PN junction, be that a diode or a BJT, as long as you've characterized it within the manufacturer or within the part number, even across multiple manufacturers, this is going to be a fairly stable figure. So this value will usually be assumed within the measurement devices themselves, so these devices that perform the current injection and the voltage measurement. However, if your part is different to what's assumed within here, you'll usually have a digital interface to be able to set a compensation register to be able to account for the difference between the part that you're using and what this part, what the device has actually assumed eta to be. So given this, we can now rearrange this equation. So it's in terms of VD. T is going to be equal to, let's see, delta VD divided by the natural log of 1 over n multiplied by Q over eta K. And you can see that we have a proportionality now. We know, like I said, what ln 1 over n is because we control n. Q is a universal constant. K is also a universal constant. And eta is assumed or is compensated from the assumed value. And since you know all of this part, and you can measure delta VD, you're able to work out temperature. So hopefully that was useful to someone. It's something that can be confusing when you first look at it, but yeah, the basic principles are actually fairly straightforward and easy to understand once you get your head around it. Anyway, thanks very much.